Hello everybody and welcome back to Business Statistics Online at Frederick Community College. In this video I will talk to you about the central limit theorem, which is a really big result and it's the foundation for all inferential statistics, and I will show you how to use Excel to solve problems associated with this topic. So before we go into solving a problem, let's talk about what this really big theorem is actually saying in plain language. It says the following, that if we take a simple random sample large enough, so that n is greater than or equal to 30, from a population with a known mean and a standard deviation, then we can say that the distribution of the sampling mean, so x bar, is normal, regardless of what the underlying population is. And the parameters will be the following. So the mean of the distribution of the sample mean is the mean of the distribution of the population, and the standard deviation is the standard deviation divided by the square root of n. Okay, and it sounds like this is not a big deal, but really this result is the foundation for all inferential statistics, and it's really a big deal. Okay, so now that we kind of reviewed what this theorem is saying, let's go ahead and take a look at an example, and we'll do an example from your online homework. And I'm going to do problem 8, and then I'm just going to show you how to do a couple other problems, but this is the main problem that I want to focus. If you can do this one, you can do all of them. So let's say what we have here. We have the following information that man spent on average $137.49 on Valentine's Day gifts, and that was in 2009. We have the standard deviation is $45, and they're telling us that the population is normally distributed. So this is actually important. Why is that important? Because we're taking a random sample of 20 men. Okay, now remember what the central limit theorem says, that the sample size has to be greater than 30. Well, it has to be greater than 30 if we don't know anything about the population. But if the population is normal, which is, it's saying right here, right? It is normally distributed, then the sample doesn't need to be greater than or equal to 30. Okay, so let's go ahead and solve this problem. I have an Excel file already set up. I have mean spending, standard deviation, and so forth kind of already prepared. So let's see what the first problem is asking. This one says calculate the standard error of the mean. So this is the standard deviation of the distribution of the sampling mean. Okay, well, let's see, can we apply the central limit theorem? The answer is yes, and we can do that because the population is normally distributed. So let's go ahead and answer this question. Yes, we can apply because the population is normal. Okay, so what is the standard error? Let's go ahead and fill this out. Mean spending, so 137.49. Okay, and the standard deviation, that's our sigma, it's $45. Sample size is 20. That's not large enough, right? But it doesn't matter because the population is normal. So we can apply the central limit theorem. So what is the standard error? Okay, that is the standard deviation divided by square root of sample size. Okay, so $10.06. Let's see, round to 2 decimal places. $10.06. That's right. Okay, next thing that we need to answer. What is the probability that the sample mean will be less than $125? Okay, so I'm asked to find probability that the sample mean is less than $125. All right, I know I can apply normal distribution. We've done that before. Okay, up to 125, my mean is the same as the population mean. My standard deviation now is the standard error, right? It is not $45. It is 45 divided by the square root of 20. And is this cumulative? Yes. So I get this probability right here, okay? Just to do a quick comparison, if you were to do the following, normal distribution, 125, mean is 137.49, right? And the standard deviation is 45. You're going to get a completely different answer. You're going to get a much bigger probability, and this makes sense because what it's really asking you is what is the probability that one person spends less than $125. This is a sample of size 1, right? So this is different than the sample of size 20, okay? So make sure that when you do these problems, you use the correct standard deviation. Okay, let's see if this is correct. So what do they want us to round to? 4 decimal places, so that's 1073. 1073. Let's check. This is right. Okay. We keep going. What is the probability that the sample mean will be more than 140? Okay. We've done a problem like that before. So probability that sample mean is more than 140. Now we need to do 1 minus normal distribution, right? We go up to 140. Mean is this. Standard deviation is our standard error. Cumulative, yes. Okay, let's just check. 140, B2, B7, 1. We get the following probability. Okay. Let's see again, 4 decimal places, so this will be 0.4015. 0.4015. Looking good so far. 2 more to go. What is the probability that the sample mean will be between 120 and 165? Okay. So 120 sample mean and 165. Okay. How do we do that one? Well, we do normal distribution up to 165, right? So this is from negative infinity up to 165. Same mean. Same standard deviation. 1 minus normal distribution. Now we go up to 120. 120, mean is the same, standard deviation same, still cumulative. Okay, so we've done similar problem like that, right? So the only difference is now you're using standard error for your standard deviation. Press enter. So that would be 0.9558. 0.9558. Oop, and I'm plugging in 6. Okay, great so far. So now we have the last part. It says identify the symmetrical interval that includes 95% of the sample means if the true population is population mean is 137.49. Okay, so what are they asking us to do? They want us to find the middle 95%, right? How do we do that? Well, remember how we found the z values that cut the distribution so that you get the 95% in the middle, right? So the values that bind 95% in the middle of the data. So how do we do that? We've done that with the inverse normal, right? So if you don't remember how to do it, let me just remind you. So 95%, okay? So if we wanted to find the values that cut it, So normal distribution, so the 95 is in the middle, which means what? What we have left is 5%, or 0.5 divided by 2, right? So 0.05 divided by 2 if it's the area under the curve, okay? And now if I were to do equals norm inverse, I want to find the z-value. 0.025, mean is, we're going to do just standard normal, right? So mean is 0, standard deviation is 1. Here's my z-score, okay? So for 95%, the z-scores are negative 1.96 and positive 1.96 because they're completely symmetric. So that means what? Our interval that contains the 95% of the data, okay, has a lower bound and an upper bound. Okay, and let me write the description here. It's the mean plus the z-value. For the lower bound, it's minus the z-value times the standard error, right? So let me do standard error. Okay, and then here it's the mean plus z times the standard error. Okay, so what is our mean? Our mean is 137.49 minus 1.96. We're taking the positive z-value times the standard error. Okay, so that's that. And then we're going to do similar. Actually, let's just go ahead and copy it and change minus to plus. Oop, something happened. Alright, let's just redo the whole thing. So this will be equal to mean spending plus the z-score 1.96 times the standard error. Okay, so that is what we get for the interval that contains 95% of the sampling mean. So let's take a look at what they want us to round it to. Round to the nearest dollar as needed. Okay, so that would be $118. That's your lower bound. Okay, and then 157 would be the upper bound. Alright, so that's that. So this is how you would approach this problem. All of these problems are pretty much the same, except that let's just take a look at the next problem. This one says what? Okay, we have the average weight of a professional football player in 2009 was this 253.9 pounds, right? And then we have a population standard deviation 25 pounds, but it doesn't tell us that the population is normally distributed. Well, that doesn't matter. The sample size is large enough. It's 36 for us to do all of the computations with normal distribution. Okay, so this problem will be similar. And then the next one, let's take a look. Again, we have, let's see, adults work on average of 1785 hours last year. The population standard deviation is given. It does not tell us the population is normal. Doesn't matter. We have 50 adults. That's a sample that's big enough. Okay, so that's what I wanted to mention in other problems. If you're not sure if you can apply it, that's always a good idea to check. Is the distribution normal? Is the population normal? Then go ahead and not worry about the sample size. If you don't know anything about it, then we have to check that the sample size is big enough. Okay. All right, so thank you for watching. I hope this was helpful, and I will see you all soon.